tomorrow is the test. The topic is centripetal force and centripetal acceleration, and the test is going to be a closed book. I'm making this tutorial to help you prepare for the test. So first you're gonna have to derive the centripetal acceleration formula. So let's start with the circle, simple circle. And let's say you have, so if you have a bucket and you attach a rope with a bucket, okay, so then you have a bucket over here at, I don't know, time t, and then bucket over here at time t1, and the bucket over here at time t2. Bucket attached to a rope, and you rotate the bucket. Of course, bucket filled with the water. So then there is a rope. There is a rope. Alright, attached to the bucket. Just because you rotate, spinning the bucket doesn't mean rope getting smaller or bigger. So rope remain the same. That means the radius 1, radius 2, radius 3, radius 4, radius 1 is equal to radius 2 is equal to radius 3 is equal to radius 4 is equal to radius. Alright, so radius is the same because the rope, the magnitude doesn't change just because you're spinning it. Alright, good. Next, there is a velocity of the bucket. So the velocity is perpendicular with the rope. So this is the velocity vector. This is we can call velocity 1. This is the velocity 2. This is the velocity 3. And this is the velocity 4. Velocity 4. Okay. A few other things. Here, this one is the length. Okay, the between this bucket and this bucket there is a length L. Okay, yeah, in the up to the delta t. Okay, so there is a delta t from bucket 1 to 2. What does that mean? At t0 the bucket is at this location, t1 bucket is at this location, and between t0 and t1 there is a length L. Okay, so what can we do? The velocity, let's talk about the velocity vector. So when you look at the velocity vector, you see the velocity vector, this one, the first one, this one, put this one over here, and then let's take the second one, put the second one over here, let's take the third one, one more I'll take, it takes the third one, right here. Okay, so and let's take the fourth one, why not? Okay, so what do you see here? You see the change of velocity. This is the change in velocity. So I'm going to write the change in velocity here. So this is the change in velocity. All right, the change in velocity. So we're going to put the change in velocity right here. So this is the change in velocity. So I'm going to put this true triangle now. I'm going to put this triangle right here, this triangle. This is also change in velocity. This is also change in velocity. And the V1 is equal to V2 is equal to V3 is equal to V. Why is that? Because acceleration you can get the acceleration two different ways. Delta V over delta t, that means change in velocity over change in time give you the acceleration. The other one is the change in direction of change in direction also give you when velocity changes the direction, that's to give you acceleration. Example. This car moves velocity, let's say velocity 10 meters per second. What would be the acceleration here? 0. This car moves velocity again 10 meters per second. What would be the acceleration here? Not 0. Why is that? Because velocity changes the direction all the time. Velocity do not changes the direction over here. That's why acceleration is 0. That's why acceleration is not 0. Get it? So there is a net force. If there was no net force, then what would happen? This velocity would be moving in a straight line with constant. Straight line is moving because there is a net force. The net force is responsible for the velocity to changes the direction. So how it changes the direction? From here to here to here to here. Okay, so we have two triangles. So you gotta put two triangles over here. Okay, so two triangle. Triangle 1. This is the triangle. So I have R1, I have R2, and I have the length. And I have this triangle. I have V1, I have V2, and I have delta V. So I'm going to use the properties of the similar triangle. So properties of similar triangle, delta V over delta L, going to give me V1 which is V, over R1 which is R. Alright, so I'm going to do cross multiplication. Delta V R is equal to V delta L. Okay, so what do you see over here? You see the time over here. So you're going to divide both sides by time. If you do that, then you will notice something. Delta V over delta T is acceleration. So acceleration R. And delta L over delta T is the velocity. So this velocity over here, okay? And this is acceleration. This is also velocity. There was a velocity here, I put it here. So AR is equal to V squared. So A is V squared over R. And we call it centripetal acceleration. We just prove it. Now centripetal force. We're going to start with Newton's second law, F equal to ma. So centripetal force is equal to centripetal acceleration. What does that mean? Centripetal acceleration is m. This one is v squared over r. So centripetal force is mv squared over r. Now one more formula I'm going to show you, and then we're going to dive into solving the problem. And that is when you have to find the force between two bodies. Okay, if you have a body over here, it exerts, and we have a body over here, the body A and body B. Body A exerts force on body B, and body B exerts force on body A, which is equal in magnitude but opposite in direction. Alright, so in 1665, Sir Isaac Newton, when he saw apple fall, he wanted to solve apple fall and moon fall problem, because he looked at the sky and he saw the moon and he was thinking, if apple fall, does the moon also fall? Now we see that, yeah, just like an apple, moon also fall. And to solve this falling apple, falling moon problem, he created the calculus, and he used the calculus to lay the foundation of physics. And also he wrote 3 laws of motion, including the universal law of gravitation. And the universal law of gravitation says that there is an attraction force between these two bodies. The one body is the mass of A, the other body is mass of B. Alright, and then the distance between these two bodies, which we call R, or you can say d squared, distance between these two bodies. And of course, there is a gravitational constant G, and the value of G is 6.67 times 10 raised to 11. Okay, so now we have these 3 formula, and we're going to use this 3 formula to solve lots of problem. So let's start the first problem. One more thing I'm going to show you, and that is the frequency and the period. So what is frequency and what is period? So if you have a circle and you start from, let's say, this dot, and you come back to this dot, what do you call it? Revolution. How many revolution? One revolution. You also can call it cycle, or you also can call it 2 pi r. It's up to you. You can call it whatever you want. So one revolution or one cycle or 2 pi r. So let's see. If you want to find the velocity of this one, velocity is distance over time. So what is the distance? The distance is this distance, and that distance is 2 pi r over t. Alright. Now when we talk about t here, t is the period, okay? And that kind of relate to the frequency. So what is frequency? So let's talk about the frequency. So frequency is number of cycle over the time, or you can write 1 over t, or 1 over hertz, or 1 over second, or hertz. Okay. And the time, the period, which symbol is t, is number of cycle over frequency, which is 1 over f, which is 1 over hertz. Okay, so which is 1 over f is hertz, which is second. Alright, so these are the two formula you need to use to solve the problem that we are solving. Now let's consider the first problem. And the rope is 0.6 kilogram, 0.6 meter. Alright, so you now spin this rope. You spin this bucket, so the bucket moves like that. Make a circle. Alright, so the radius of the rope is 0.6. So this is your hand. Okay. Alright, now what we are trying to find? We are trying to find the centripetal acceleration. How can we find the centripetal acceleration? Okay, let's first find the velocity. So what would be the velocity? Velocity would be 2 pi r over t. Alright, now let's say that makes two revolution every second. Alright, you make 2 revolution every second. So I gave you the frequency. So let's first take care of frequency. So frequency is number of cycle over time. So then frequency is 2 revolution. 2 revolution does not have any SI unit, so don't write it. 1 second. So then frequency is what? 1 over second. And then is 2 hertz. 1 over second is hertz. Don't forget that. Okay, now we're gonna find the period. Period is cycle, number of cycle over, of course, the frequency. So frequency is 2 hertz, and cycle is 1. So is 1 over 2, 1 over hertz. 1 over 2 is 0.5, 1 over hertz is second. Alright, so its period is 0.5 second. Okay, now velocity. So you can find the velocity. How can we find the velocity? Let's find the velocity here. So velocity is 2 pi r over t. So velocity is 2 times 3.14 times radius is 0.6, and the t is 0.5 squared. So velocity is 7.5 meter per second. Now we got to find the centripetal acceleration. So centripetal acceleration is v squared over r. So 7.5 squared over 0.6. So centripetal acceleration is 95 meter per second squared. Now we're gonna find the centripetal acceleration on the moon due to Earth. Okay. So now make a prediction. What do you think? The centripetal acceleration, the acceleration on the bucket is more, or the acceleration on the Earth is more? Okay. So make a guess before. Pause the video and make a guess. So now there is a moon, of course. There is a moon and there is Earth. and the distance between moon and earth is 3.84 times 10 raised to 8 meters. We want to know the acceleration, the centripetal acceleration of the moon to earth. Okay, that's what we are trying to find. So how can we find it? Let's start with d. D is because the moon is making some. D is rotating like this around the earth. So d is velocity is distance over time. Right. So the distance is 2 pi r over time. Okay. All right. So now what do we also know? Acceleration. That's what we want to find. Acceleration is v squared over r. All right. So we can write v squared 1 over r. So what is v squared? V squared is 2 squared, this is 4, pi squared, r squared, and t squared. And don't forget 1 over r here. Okay, so what else you can do? R goes to r squared is r times. So this is 4 pi squared r over t squared. So this is the acceleration, centripetal acceleration of the moon. So let's calculate it. So 3.14 square, and then r is the radius of the moon, 3.84 times 10 raised to 8. Alright. And divide everything by t square, and t you already know that it takes 27.3 days. It takes 27.3 days for the moon make one revolution or one cycle, or to move 2 pi r. Okay, so good. But days is not as a unit, so we're gonna make this guy the SI unit. So now days is on the downward stairs, so days cancel. So 1 day is 24 hour times. We need second on the top and then hour on the bottom. So 1 hour is 3600 seconds. So day cancel, hour cancel. So 27.3 times 24 times 3 is 28 times 10 raised to -4. Alright, so then I have 2.8 times 10 raised to -3. Find the force between moon and earth. So there is a moon and there is earth. Alright, so this is earth, this is moon. You're gonna find the gravitational force between moon and earth. So what is it? So the gravitational force, never forget, there is a distance between moon and earth. This is 3.84 times 10 raised to 8 meter, and the mass of the earth is 5.98 times 10.24. Mass of the moon is 7.25 times 10 raised to 22. Okay, all right. So Newton universal law of gravity tells us Z m moon m earth over distance squared. So G is 6.67 times 10 raised to -11. M is 5.98 times 10 raised to 24, and the mass of the moon is 7.25 times 10 raised to 22. Everything divided by, I don't know, R, and R is the distance 3.84 times 10 raised to 8 squared. So again, A times 10 raised to B. Okay, so what are your A? A is 6.67 times 5.98, and then you have 7.25, and then you have 3.84 times. You have 10 raised to -11. You have positive 24, 10 raised to -27 plus 6, 4. So 19.6 times 10 raised to 6 raised to 19. So so this is gonna be 1.96 times 10 raised to 20. A 5 kilogram object move clockwise with, I don't know, with a 5 kilogram object move clockwise, I don't know, so let's say move 20 meters per second, and the radius is 25 meters. Alright, so what do you want to find? The centripetal acceleration. So centripetal acceleration would be v squared over r. So v squared would be 20 squared, which would be 400. Alright, and r would be 25. So 25 goes to 400 once, and then 156. So centripetal acceleration would be 16 meters per second squared. What about the centripetal force? Centripetal force would be MAC. So centripetal force would be M is 5 times AC is 16. So this would be 80. Now we're going to draw the vectors. We're going to draw the velocity vector and centripetal force vector. So this is the velocity vector, and this is the centripetal force vector, and they are perpendicular with respect to each other. We're going to find the velocity. So this object moves, I don't know, 1200 revolution. 1200 revolution means 1200 times. So 1200 revolution, 1 hour. Right? 1 hour, it makes 1200 revolution. The same object. We want to find the velocity. We know the velocity vector at that direction, but we want to find the size of that velocity vector. How can we do that? So let's talk about the frequency. So the frequency is number of cycle, 1200, and hour, which is the number of cycle over the time. So 3600 second. All right. So now you have 1/3, 1/2. That means 1/3 is 0.3, and 1/2 is hertz. Okay, good. All right. Now we're gonna have to find the period. So the period is number of cycle, 1 cycle, and number of hertz, 0.3 hertz. So 1/0.3, 1/hertz, 1/0.3 is 3, 1/hertz is second. So period is 3 seconds. So now we can find, of course, the velocity. Velocity is distance over time, 2 pi r over t. So velocity is 2, pi is 3.14, and so velocity is 21 meters per second. Find the acceleration due to gravity on the satellite. So what is the hypothesis? The hypothesis here is, I'm going to give you 3 examples. These 3 is the Earth, and this is the Earth center. This Earth, you are here on the surface. This Earth, you are here on the surface. This is Mount Everest. And this Earth is you just the infinite distance away from the center. Here, of course, g is 9.81 meter per second square. Here, g is less than 9.81 meter per second square. Here, g is approximately 0, or g goes to 0. This is what we are trying to solve right now. We want to see what would be the acceleration due to gravity on a satellite that is 100 million meters away from the center of the Earth. The acceleration due to gravity is always measured from the center of the Earth. Why is that? Because the Earth center pulling everything to its center. Okay. All right. So, all right. So let's get it done. What are we talking about? We are talking about the Earth. So this is the satellite. and this is Earth. The Earth mass, and this is satellite mass. We don't need satellite mass, by the way. Okay, let's give you an example. So for example, if I drop it here, what is the mass of this marker? The mass of this marker is 9.8. If I double the size, by putting a tape on it, right? If I double the size by putting a tape on it, so what would be the acceleration due to gravity? Of course, 9.8. Just because you double the size doesn't changes the acceleration due to gravity, because the gravity doesn't depend on the mass. The falling body doesn't depend on mass. It depends only on where it's falling to. In this case, it's falling to the Earth. We have to